The shape of a finished component and the material from which it's manufactured can be a very limiting factor when it comes to the method you're going to use to produce it. Casting metal to a specific shape or forging it from hot billets are just two examples where the function and the performance of the component almost dictate the production technique. Cost is, to some extent, of secondary importance. But there are many components which can be made easily and cheaply from sheet metal. All sorts of motor car parts. Domestic appliances like washing machines, fridges, radiators. Anything really, from tin cans to metal baths. All can be made by press working. If the pressing process hadn't been perfected, a lot of these things would be extremely difficult to make and extremely expensive. Objects produced from presses are uniform and highly accurate, each piece identical to the one before it and the one after. It's a technique which gives production engineers a great deal of flexibility, and it's ideal for mass production. By and large, finishes are smooth, the pressing can have considerable strength and rigidity, and you don't waste too much raw material. Most press operations demand specific tooling. Tooling up is an expensive operation, and you can only do it if you're going to produce enormous quantities of a particular object. The most popular metal when it comes to pressing is mild steel. It's still fairly cheap, and so far seems to have the edge on aluminium and plastics, except for certain specialized functions. In this program, we'll be looking at the pressing opportunities offered by mild steel. But the techniques apply to other materials as well. The key to successful press working lies in the press tools themselves. This is a simple tooling setup. The top half of the tool is called a punch. At the base, there's the bolster, which supports the die. This will reflect the shape of the pressing, and it's usually made from a hard-wearing material like a hardened alloy steel. The other half of the tool, the punch, is moved usually downwards to punch out the component from the metal strip. The punch, in this case, is attached to the ram of the press by the punch plate or holder. The cutting out of the metal shape from the strip is called blanking. The strip is brought in as cold-rolled coil. It's a convenient way of providing a large quantity of material in the smallest possible package. The strip is passed through a set of straightening rolls to this simple single-action power press, which punches out a series of circular blanks. Blanking these out one at a time from a single piece of strip would be wasteful and uneconomic. So they've increased the width of the strip by 1/2, and so doubled the number of blanks obtained from a given area. The whole idea of a blanking layout, and hence the layout of the die, is to secure the maximum number of blanks from the minimum amount of metal. You can see there's very little waste left here. One drawback when you press a blank is that you can get burring of the edges. If the piece has to perform a precise and delicate roll, as this car seat adjuster mechanism has to, then you'd have to deburr each component after it's been blanked, and that would be time-consuming and cost a lot of money. Quite recently, there's been a new refinement, which makes it possible to produce components in one single press which have no burring at all, and therefore don't need any finishing. It's done in a single operation in this triple-action press. The technique is called fine blanking. The strip metal is a fine-grained mild steel. It is this fine grain which will help ensure a fine edge to the finished article. The steel is unwound from the coil and straightened before it's fed to the press. It's held firmly in position, and the die then closes, and the material is further secured through a counter pressure. It's clamped firmly into its final position by a gripper ring embedding itself into the base of the material. The punch then forces the component into the die. As the ram reaches its topmost position, the counter pressure and gripper pressure are removed and the operation is completed. The locking counter pressure ensures that the surfaces are sheared finely and accurately. The tool then opens, the scrap strip is removed, and the slugs and the finished component are ejected by air blasts. The whole system is guarded by a magic eye. If anything or anybody accidentally enters the machine, the magic eye beam is broken and the machine stops instantly. This is a pressing technique that's becoming more and more popular. At the moment, there are over 1,000 fine blanking presses in the world. They supply components for everything from cars to office equipment, penknives, even watches. Another common presswork operation is bending. Often, it follows on directly from blanking. These brackets are part of a fire extinguisher, and they've been curved on the simple power-assisted fly press. During the bending operation, the shape of the metal piece is changed without altering the overall dimensions of the metal. The metal is deformed, but not stretched. If the material hasn't been annealed, then any bending operation must be done at 90 degrees to the grain flow. If the bending is done parallel to the flow of the grain, then the material is liable to crack. Another operation which follows blanking is forming or drawing. Here, the blank sheet of metal is drawn by a moving punch into and through the bore of a die to form a hollow shell. In this case, the thickness of the wall is substantially the same as the blank. The gap between the punch and the die is designed to be very close to the thickness of the domed or drawn material and virtually the same as the original blank. You obviously need metal with good ductility, the ability to be drawn out without being impaired in any way. This is particularly important when you move on to deep drawing. This technique is used to make hollow objects, which can be shallow or deep, like the bodies of fire extinguishers or small gas cylinders. These cylinders are for the shell of a small fire extinguisher, and they begin life as discs of mild steel. They're coated with zinc phosphate and soap to lubricate them. A ram pushes the disc through a series of rings. The first ring, the intake ring, forms the cup, and this is subsequently ironed by a number of ironing dies. The dies are made up from tungsten carbide inserts fitted in high-strength steel housings. Obviously, the cost of dies and machines is high, but the end product has a high standard of accuracy and a superb surface finish. With tool sets in both ends of the machine, allowing drawing operations to be carried out on both the forward and return strokes, 800 cylinder cases an hour can be produced. If complex shapes are required using presswork, then the shape is built up gradually in a series of single press operations. Take the cover for this car brake servo system. The original press produced a circular metal blank. Then the blank is drawn into a dome shape. The next operation is a reverse draw. This is necessary because it's difficult to create a raised impression on such a large blank. Then the remainder of the body is drawn out and the nose is knocked out or pierced. Then there's another drawing operation to finish off the pressing. The shape of the servo cover is now recognizable. Now it's time to clip away or crop the unwanted material. Finally, 4 small holes are pierced in the finished part, which forms 1/2 of the complete servo cover. All these individual press operations take place at every single stroke of this 400-ton single-action mechanical press. The transfer between each station is done by hand. This is a time-consuming, boring, mindless, and an expensive chore. Where very high output is demanded, over 20,000 components an hour, it's totally impractical. The answer lies in the transfer press. Transfer from one operation to the next is done automatically. This transfer press is being used to produce the tops or cones of aerosol cans. In 8 separate and different press operations, the simple dome-shaped blank is gradually transformed into a finished cone for the aerosol can. The cycle starts when the cold-reduced tin plate is slit into this pattern to save as much metal as possible. Each sheet is cut up into 4 thin strips. Now it's ready for the first step. In this double die strip feed press, running at 230 strokes per minute, the component is blanked out and drawn. The small amount of waste material left behind proves how valuable the initial cutting of the strip metal was. The next 8 operations are carried out in the 8-station pillar die set tool. The first station executes a redraw and prepares the material for the second operation, a redraw and trimming to the finished outside diameter. The third is a redraw and the initial curling of the outside. 4, a redraw and finishing of the curl. 5, scores the cone. 6, pierces the hole in the top. 7, curls the aperture. The 8th and last station finishes the top off by collapsing the snap block. The complete tool set is made from high-quality hardened alloy steel and costs £28,000. The high cost is justified by the enormous output. You can make some 35 million components before the die wears out. When you have so much money tied up in a piece of machinery, you have to treat it carefully. Misfeeds, which could cause a lot of damage, must be prevented. Now that's done by infrared sensors which look and confirm that each component is in its place. If one isn't there, the press is stopped before it goes over bottom dead center, causing a lot of damage. The finished cone and the body of the can meet up here for their final marriage in the largest aerosol can-making unit in the world. For large pressings, which have to be turned out in great numbers, like the sides of the Metro, a continuous line of separate presses has to be used. The advantage of these huge presses is that they eliminate a series of individual operations. And at the end of the process, produce a complete side panel, perfectly shaped from the front door hinge pillar to the tail lamp corner. The panel begins life as coiled strip steel. It's straightened and then cut into strips and blanked into preforms by this 600-ton single-stroke press. These blanks are then the feed, which will move slowly through the hydraulic presses. They cost over £6 million and are amongst the most advanced in the world. The initial shaping is done by a 1,600-ton double-action press. In the first action of the press, the metal blank is trapped and held securely in position. The second action of the press forms the master shape. It's known as the main form. The second press, a single-action 800-ton mechanical press, finishes off the main form. It's called a restrike and ensures that the dimensions are completely accurate. You can see that the window spaces and the wheel arches still remain to be cut out. And this is done by the third press. What's happening is that as the blank goes through the presses, more and more metal is removed and more intricate shaping takes place. It would be nice if you could do the whole operation at one stroke, but no single press is capable of creating large, complicated components like this in one operation. In the fourth press, the post section is formed and the face for the door lock is pierced. The fifth press finishes off the trimming and pierces the holes for the door hinges. The entire operation is computer controlled. Walking beam parallel carriers lift and pass the body panels from one press to the next. Then the last of the presses molds the final form for the front pillar and the rear tailgate. When flat out, the line of 6 presses can make 480 of these panels in 1 hour. It's an impressive sight when in full flow. In general, provided the material to be worked is soft and ductile, and the high cost of the equipment can be justified by a correspondingly high output, forming metal by press working really can pay big dividends.